So I'm going to split apart 7.1 over a course of several days. So 7.1a, we're going to talk about simplifying trig expressions. All in Unit 6, we did trig problems, solving triangles, angular speed, sectors, all that fun stuff. But we used a lot of geometric knowledge. We had to use knowledge about, alternate interior angles, the sum of the interior angles of a triangle, that sort of stuff. Unit 7 is the analytical side of trig. It's the algebra part of trig. And today's goal is to use algebra, factoring, completing the square, maybe finding the common denominator, all that stuff, all your algebraic knowledge, in addition to trig identities to simplify trigonometric expressions. In other words, we're going to take complicated looking expressions and break them down into something that's a lot simpler. To do this, we need to know some trig identities, which I think we already covered in Unit 6. So let's just refresh our memories on some of the fundamental trig identities. So I would wager that half of what I'm going to write down should be review for us, and the other half we might have already known, but we just didn't put a name on it. The first I want to cover are called the reciprocal identities. These are the facts that relate the trig functions to each other via reciprocals. In other words, we should know that cosecant of anything, of theta, by definition, is the reciprocal of sine. Secant of theta, by definition, is the reciprocal of cosine. And cotangent, by definition, is the reciprocal of tangent. In addition, we should know that tangent is the ratio of sine to cosine, which means if cotangent is the reciprocal, it should be the exact flip. Cotangent is the ratio of cosine to sine. The other identities that we talked about in Unit 6 were the Pythagorean identity, which was just the trig version of a squared plus b squared equals c squared. That said that if you have cosine squared and you add it to sine squared, it'll always equals 1. But we had two other variations that came about when you divided these guys by either a sine squared or cosine squared. So if you divide everything by a cosine squared, you get 1 plus tangent squared equals secant squared. And if you divide the original identity by sine squared, you get cotangent squared plus 1 equals secant squared. So these should be stuff that we already know. The next two sets we did not explicitly cover in Unit 6, but it should be very common sense. Let's write them down first, and we'll talk about where they come from, and let's talk about the logic. So the next set is called the even-odd identities. And these basically tell us what to do when we input a negative angle. So if you take a sine of a negative angle, that's the same thing as the negative of the sine of a positive angle. If you take a cosine of a negative angle, well, that's just the same thing as the cosine of a positive angle, nothing fancy. And if you take the tangent of a negative angle, that's the same thing as the negative tangent of the positive angle. Now, although this may seem like new to us, we've actually covered this logic, and again, I'll talk about that later. And the last set I want to talk about is the cofunction identity. And this says, if you take sine of pi halves minus an angle, that's the same thing as cosine of the regular angle. Now, you could easily change the pi halves into 90 degrees if you're in the degree system. All the identities that I'm going to write down, though, I'm going to use the radian system. And of course, you can flip things around. If you take cosine of pi halves minus the angle, that's the same thing as sine of the original angle. And then there is a parity of the other four trigonometric functions. If you take the tangent of pi halves minus an angle, that's the cotangent of an angle. If you take the cotangent of pi halves minus an angle, that's the tangent of an angle. If you take the secant of pi halves minus an angle, that is the cosecant of the angle. And if you take the cosecant of pi halves minus theta, that is the secant of the angle. So these four sets, the reciprocal identities, the Pythagorean identities, the even-odd identities, and the cofunction identities, there's no way around it. We simply need to know it. So I don't do whatever you need to. Make flashcards, write these guys down, 100 times. Do whatever you need to do in order to know it, because these are basically the laws, the rules that allow us to manipulate trigonometric expressions to today's lesson goal, to simplify them. Now let's talk about the even, odd, and cofunction identities for a moment. So I'm going to go off on a, pardon the pun, tangent and talk about where these guys come from, because they look intimidating. Oh my goodness, you're telling me I have to memorize all of this? Yes, but if you understand or know what's going on, you don't really need to memorize. Why memorize when we can understand? So let's talk about the logic behind the even, odd identities. We need to recall something that we talked about in Unit 6, that on a coordinate system, x relates to the cosine of an angle and y relates to the sine of an angle. Right? So let's take a look at what the even, odd identities say. If I put a negative angle inside of a sine, I get a negative sine. If I put a negative angle inside of a cosine, I get the same cosine out. Negative angle, negative tangent. So the even, odd identities relate to what happens when my angle is negative. Well, let's see that visually. Well, I guess that's the only way we can see things visually. That's redundant. So you should know that negative angles are angles that are measured, sorry about that, clockwise. So let's take a look at a negative angle here. So that is negative of an angle. We can see here how in this quadrant, quadrant 4, we have positive x's and negative y's, or in other words, positive cosine and negative sine, because as we said before, x relates to cosine, y relates to sine. Let's see how this point here, this negative angle, relates to his positive twin. Well, his positive twin would be up here. Let me do a different color here. So instead of going negative theta, let's go positive theta. Right. Well, I hope we can see here that this is a positive x, positive y, or in other words, positive cosine and a positive sine. So notice how these points here are sort of like vertical to each other. What this says here is that the x's will relate to each other and the y's will relate to each other because they're basically the same angle if you take a look at it in terms of references. So we know that for a negative, or I guess a little mistake down here, these aren't, well, yeah, they're positive thetas here. Right. We can see here how, close it, if you take a negative angle, right, the cosine stays the same. But if you take, if you look in terms of sine, how do these sines relate? Oh, you can't see that. How about this? A little bit better. You can see that the sines are exact opposites of each other. And that's what the even, odd identity can be thought of. It can be thought of comparing what happens to sine and cosine when you make the angle negative. And that's basically comparing the sines and cosines between quadrant 1 and quadrant 4. Now, where do we get the tangent relationship? Well, remember that tangent is just the quotient of sines and cosines. So if we're in the negative region, if I were to divide those two guys, negative sine divided by positive cosine, of course we get the negative tangents. So from this picture, we can see that if I take the cosine of a negative angle, right, what do I get? Well, it's the same thing as a positive cosine. If I take the sine of a negative angle, so instead of looking at quadrant 1, I'm looking at quadrant 4, what do I get? I get the negative sine of an angle. And of course, if I take the tangent of a negative angle, it's just taking these two guys dividing by each other, and that's going to give us a negative answer. So that's where the even odd identities not necessarily come from, because they come from the actual graph itself, but this is a way to visualize the even odd identity. So yes, you need to memorize it, but understanding what they say makes memorizing it a lot easier. Now, the logic behind the cofunction identities is actually pretty cool. Have you guys ever wondered what the word in cosine, cosecant, cotangent really means? Well, the co of cosine, cotangent, and cosecant stands for complementary. And in geometry, the word complementary means adds up to 90 degrees. Why is that important? Well, remember that in a right triangle, which is what we all study when we do trig, the non-right angles are always complementary to each other. So if this guy is theta, this angle up here, phi, has to add up. Both of these guys have to add up to 90 degrees, or pi halves radians. So if this guy is theta, how would I calculate what this angle is? You would just subtract him from 90 degrees, or in other words, subtract it, if we're in the radian system, from pi halves radians. So that's where, in the cofunction identities, we get this very weird expression here. Pi halves minus theta literally says the complementary angle of theta. Right. So I guess that's important enough. Pi halves, wrong color. Pi halves minus theta translates to the complementary angle of theta. Well, what does it matter? Well, let's go ahead and do some labeling here, right? So let's just call this A, B, C. So this is side A, side B, side C. And let's just look at one function. We can see that sine of theta, opposite of our hypotenuse, is A over C. Cosine of theta is B over C. Tangent of theta is A over B. Let's do the same thing for the complementary angle. What is sine of the complementary angle? Pi halves minus theta. Well, it's opposite of our hypotenuse still, but we have to focus on this angle. Opposite of our hypotenuse would be B over C. Cosine of the complementary angle is adjacent over hypotenuse. And then the tangent of the complementary angle is opposite over adjacent. I guess I need to do one more, cotangent. Cotangent is what? B over A, and cotangent of the complementary angle is adjacent over opposite A over B. And I hope you can see some relationships going on here. A over C, A over C. So these guys connect. B over C, B over C. These guys connect. A over B, A over B. These guys connect, and then these guys connect. So what does it say? It says that the sine of an angle is the cosine of the complementary angle, and that should make sense because co means complementary. So the sine of the complementary angle, cosine, is equal to the regular sine of the regular angle. So that's all that really says, that the sine and cosine relate to each other. The tangent and cotangent relate to each other. I'm not going to bother with secants and cosecants. I think you guys get the idea. So cosine literally means the sine of the complementary angle. And that's all that the cofunction identity really say. So I will admit, as a student, I first just memorized it. And I'm guessing that's the route you're going to have to take. But after a while, after you get used to it and after you use it for a while, it actually makes pretty much sense. So here's the downside, or here's the bad news about this lesson. It's not anything you can solve. It's not a formula. It's not a you got to do this every single time. It is 99% logic and 1% knowing your identities, knowing your algebra. So I can't really give you a blueprint on how to simplify trigonometric expressions. The only way we can get better at this is if we practice. But I do believe seeing some worked out examples can help you. So for the rest of the video, for the rest of the notes, I'm just going to do a handful of random examples. Heck, I might even pull it straight from your practice. There's nothing special about these examples, but just seeing more and more solved in front of you gets you exposed to lots of ideas, lots of thought processes, and lots of techniques, and that's the only way you can get better at being a mathematician. So let's just do an example here. Suppose I ask you to simplify cosine of theta plus tangent of theta times sine of theta. I do have some general hints, though, and these are the things that I think about. The first thing I look for are squares. If I see squares, I normally think of Pythagorean identities. But in this case, there aren't any squares, so I can't use Pythagorean identities. So here's my hint or tip to you. When in doubt, convert into sines and cosines. This is usually my method of last resort. I always try to use identities first. I try to use, if I see, tangents on top, tangents on bottom, I'll just cancel them out. But if I have absolutely no idea what to do, I would just convert to sines and cosines. And that's basically my only choice here. Because there's no squares, I can't use Pythagoras' identities. So what does this guy equal? Cosine, of course, stays as cosine. And we should know that this tangent here, by definition, is sine over cosine. And of course, I still have this sign here. Then we just do regular math, right? Sine times sine is sine squared over cosine. Notice we're left with a fraction, right? And analytical trig, this whole unit is all about using algebra knowledge with trig expressions. So just because we're using sines and cosines doesn't mean we can ignore basic number sense. What are we doing here? We are adding fractions, right? We have cosine over 1 plus sine squared over cosine. We have a non-fraction plus a fraction. How do you add fractions? You got to find the LCD. So hopefully here we can see that the LCD is just cosine theta. So we're going to multiply everything, or rather, we're going to try to get the denominators to be cosines. So I don't have to do anything with this guy because he already has a cosine, but I'll go ahead and multiply this guy by cosine over cosine. So that's going to give us cosine squared theta plus sine squared theta all over cosine, because they have the same denominator now. And lo and behold, what do we know? Cosine squared, sine squared, this equals 1. So we have 1 over cosine, which is secant. That's pretty cool. This whole guy here at the beginning equals secant. So notice, it is trig. We are using sines and cosines, but this problem is 90% algebra. And that's what you got to do. Flex your algebra skills. Let's do another one here. Again, there's nothing special with these examples. I'm just picking them randomly. But the more examples you see, the more practice you do, this is the only way you can get better at it. So let's say I wanted to simplify this guy. Again, I don't see any squares, so I can't use Pythagoras' theorem. But I do notice I'm doing fraction plus a fraction, so let's add these fractions together. The technique is to add fractions, they need to have the common denominator. So the left fraction needs a 1 plus sign. And then the right fraction needs a cosine. Here's my tip to you, take it or leave it. I typically leave the denominator in factored form. 9 out of 10 times with these fractional problems, you're going to have to do some cancelization, and it's easier to do and it's easier to see when it's left in factored form. Again, will this work all the time? No, but it's a good place to start. So if I do leave in factored form and there's nothing seemingly that I can do, that's when then I go ahead and multiply it out. But I do go ahead and multiply out the numerators. So you have sine times 1 is sine. Sine times sine is sine squared. Cosine times cosine is cosine squared. And then on the bottom, again, leave everything in factored form. Because we should see, hey, we got squares here. This equals 1. And we have sine plus 1 over cosine times 1 plus sine. And knowing that addition is commutative, sine plus 1 cancels out with 1 plus sine, and that leaves us with 1 over cosine, which gives us secant. Again, that is pure coincidence, guys. It's not always going to equal secant. Right. So there you go. There's an example of simplifying. And what knowledge did I use? Yeah, I did use a bit of trig here. That's Pythagoras' identity. But we started off with an algebra concept, adding rational expressions. Feel free to stop this video at any time if you think you got the hang of it. I'm just going to do 1 or 2 more examples. Again, there's nothing special with these examples I'm picking. They're just random examples. The more you see and do, the more you learn. So I'm going to pick a random example from your homework. Say, let's do this one. Simplify sine to the 4th theta minus cosine to the 4th theta plus cosine squared theta. So I do see some squares, but I do see to the 4th power as well. So I could use Pythagoras' theorem here, but I really want to see a sine squared. So it seems like I'm stuck. Well, when in doubt, convert to sines and cosines. Well, too bad. They're already sines and cosines. What can I do? Remember, we can't forget regular algebra. We should notice that although this is to the 4th power and this is squared, I got multiple terms of cosines. Both of these guys have cosines in it. So if they both have cosines, we can factor it out. We might have to use some factoring here. So this equals sine to the 4th theta. And since there's a minus here, let's factor out a negative cosine. And I want to factor out as many cosines as I can. So we'll factor out a cosine squared because I know both of it can fit. That'll leave behind a cosine squared theta minus 1. Now, that seems to be a bit messier, but anytime you see a squared with a 1, we should think of Pythagoras' theorem. So we need to remember that cosine squared theta plus sine squared theta equals 1, right? I don't want, I'm trying to, your goal is to rearrange this guy so it looks like what you have. And I hope it doesn't take a lot of algebra to know that I can subtract the 1 over and subtract the sine squared over. So here we have cosine squared minus 1 equaling negative sine squared. And that can be substituted directly. So this equals sine to the 4th theta minus cosine squared theta times negative sine squared theta. So that is sine to the 4th theta plus cosine squared theta sine squared theta, because a negative times a negative is positive. And it looks like we're stuck again. Well, we'll do the same algebra trick, right? We should notice that these guys here both have a sine squared. So let's factor out a sine squared. That'll give us a sine squared plus cosine squared. And there's no more sines because we took him all away. And what do you know? We have Pythagorean identity. So this guy here should equal 1. So this whole guy should just equal a sine squared, right? So this ugly mess equals a plain old sine squared. Yeah, again, we did have to use trig. We used Pythagorean identity here and here, but the bulk of it, the heart and soul of this problem is just straight up algebra. And again, I hate to say it, the only way you can get better at this is if you practice. For this video, let's just do one last example. Suppose I wanted to simplify, I don't know, cotangent of a minus 1 over 1 plus tangent of negative a. Right? Well, the first thing I notice is I have a negative angle. So let's just take care of that quickly with the even-odd identity. I know that the tangent of a negative is the negative of the tangent. So next, I notice I'm dealing with reciprocals. One is cotangent and the other is tangent. So I know I can flip one of them. It really doesn't matter which one we flip. I'm going to go ahead and change the cotangent into 1 over tangent just because I feel like it. There's no rhyme or reason to this. It's just simply because I feel like it. Now, this does bring us to a problem here. It creates a compound fraction. Notice we have a fraction within a main fraction. So let's think back to the previous unit, the technique to simplify compound fraction. I like to clear the fraction. So we're going to multiply everything by the LCD. But we only have one denominator, it's tangent, so that's going to be easy. So this guy gets times by tangent. This guy gets times by tangent. Times by tangent. Times by tangent. Now, I'm actually going to multiply the whole thing by tangent. I'm feeling lazy here. Just go ahead and do that. So we can see in the numerator, the tangents cancel out. 1 times tangent is tangent. And you can see why I left it in factored form. Again, it's just a weird algebra math thing that the denominators, you typically leave it in factored form because 9 out of 10 times things will cancel. So we can see here that the 1 minus tangents will cancel, leaving behind a 1 over tangent, which of course we know is cotangent. Right? So this ugly looking fraction simplifies to a simple cotangent. Again, I said it probably 4 times in this video. I'll say it 1,000 times in class. There is no trick to this. There is no formula. There is no blueprint. You just have to practice. You just have to do it because it is just algebra, algebraic manipulations. And the only way you can get better at it is if you practice. So good luck.